Welcome to my presentation about unit testing for software engineering. My name is Thomas Freeman. I hope you all enjoy this video. I certainly learned a lot about unit testing by creating this presentation, and I hope you all learn a lot too. So, without further ado, let's begin. So, what are we testing for when it comes to software testing? Well, we're looking for software faults. So there's a few different definitions of exactly what a software fault is. So I'll tell you what a software fault is not. A software fault is not the failure of the software itself, and it's not simply just an error or mistake. A software fault is something wrong with the design of the software or something wrong with the machine itself due to an error in the design or manufacturing process. So as you see down here in the bottom, errors are essentially your typos or whatnot that create faults. Now, fault is something wrong with the algorithm itself, and then that fault will manifest itself as a failure. Now, a failure is what we see when a fault occurs. It's the wrong behavior, it's the malfunction due to the activation of a fault. So what is a software fault? Well, I found a really good academic paper. It was called Software Faults, a Quantifiable Definition by these researchers called Munson, Nakora, and Sheriff. They were from University of Idaho, California Technological Institute, and California State at Fullerton. So kind of a collaboration of a few different universities. And they were saying, by definition, a fault is a structural imperfection in a software system that may lead to a software's eventual failing. So here's the thing. A fault is an imperfection within software. Every software has faults. It doesn't necessarily mean that it's going to break it and burn it to flames. But at the same time, you might not ever see a failure caused by a fault. It may lead to eventual failing, but oftentimes faults are not necessarily known for a while until some user implements some crazy edge case that eventually is found. So how do you quantify faults? Well, I was just reading from the paper itself. In this paper, we base our recognition and enumeration of software faults on the grammar of the language of a software system. So if you've taken Dr. Ligotti's compilers class, which I highly recommend, it's a great class, we talk about grammar of programming languages. So, for instance, in this paper, you're mainly dealing with syntax errors, something that violates what constitutes a valid token within the language itself. It says, by tokenizing the differences between a version of the system exhibiting a particular failure and a version in which changes were made to eliminate that behavior, we're able to unambiguously count the number of faults associated with that failure. So that's kind of an interesting point, because this paper doesn't necessarily estimate the number of faults that could exist within a system. It's specifically talking about the number of faults that were found within this software system, and then code was made, pull requests were made that actually changed the behavior of that software, and counting the number of those bugs. So this is very unambiguous, and it quantifies the number of faults. So we'll look at a pretty simple example here. I wrote this in C# within Visual Studio. So the idea is here that we have we have three characters that are in a string array called chars. Now the idea here is that we want to create an algorithm that's going to loop through them and print A, then print B, then print C, and then stop. Well, I'm sure you can pretty quickly see what's wrong with this code here. Here, we're going to try and print out 10 different elements of an array. So it's going to start, arrays are indexed to 0, so it's going to go ahead and I equals 0, it's going to print out A. Excuse my mouse art here. I equals 1, it's going to print out B. And I equals 2, it's going to print out C. But what happens when it prints, or tries to print, index 3? Well, there isn't an index 3. We don't have, character D, or what might be the fourth element. So it's going to cause a failure. So this line right here is the actual fault itself, and it's going to create a failure, as you'll see in this slide. So yeah, index out of range exception. So this failure occurs, and it's pretty much saying, hey, you tried to print element number 4, but there isn't element number 4. I'm sure we've seen this error a million times. It's something every computer science student will have to struggle with a little bit to understand array indexing and all that. So this was pretty expected. And this would just be a really simple type of fault here. But what other faults are there? Well, there's incorrect input type. So say you expected a string, but instead you received an integer, or there's an out-of-memory error. The machine, only has 100 megabytes of memory, and you try to allocate 120 or something. That was a lot more common back in, well, before, 2000 or so, whenever memory became really cheap. You would have to really, really be concerned about how much memory you're using. Today, not so much a big issue. There's also segmentation fault. Technically, this example we just saw was a segmentation fault where it tried to access some memory that was out of the bounds of what was appropriate for this program to be accessing. So those are some of the different examples of segmentation faults. Now, what types of faults are there? There's algorithmic faults. This is something wrong with the algorithm itself, not setting loop conditions that could lead to an infinite loop, stuff like that. There's precision faults. So let's say you're working with banking software. You need to keep track of cents really precisely, but you accidentally use an integer, so you only have natural numbers. Well, you could lose a lot of precision not using cents. There's documentation faults. So these ones won't normally lead to an error. This is more like a human issue, whereas your documentation might say your code behaves in one way, whereas in reality, your code behaves in a completely different manner. There's overload faults. You're putting too much stress on a machine. Not too common with modern web applications and the like, but definitely an issue when it comes to scientific modeling software like weather modeling. For instance, we'll use a lot of floating point calculations, which will put a lot of stress on CPUs, and so you need to have a pretty strong system. But that's not always undesired. For instance, I forget the name of it, but there's a program that essentially tries to find higher and higher prime numbers. Well, it's pretty simple to do up to, maybe the digit 1,000, but once you start talking about prime numbers that are, 6, 7, 8, 9, 10 digits long, that puts a lot of stress on a machine. It's actually pretty good a way to load test a new machine. If you have a new machine, you want to make sure that your cooling systems work well. Try and calculate a bunch of prime numbers as high as you can, and you'll pretty quickly max out your CPU, and you'll be able to kind of get a benchmark of where it's at. There's capacity faults. It's similar to overloading faults. Your system requests more resources than your operating system can handle. There's also coordination faults. So these are resources that are not available at the time of the request. So pretty popular example of this is the Dining Philosophers program or problem, implemented and solved by one of my favorite characters in all of computer science history, Edsger Dijkstra. Really, really interesting character. If you have a second, go to his Wikipedia article. For instance, you'll find out pretty quickly that he never really used computers. Funny enough, one of the more popular computer scientists wrote all his proofs in ink. So you can get an idea of how crazy that guy is. But interesting. Anyways, he created this program called the Dining Philosophers problem, where you have 5 people on a circle who are trying to eat the food in front of them, but in order to eat, they have to use 2 forks. Well, we have 5 people and 5 forks, but we don't have 10 forks, so essentially the idea is that you need to allocate your resources and such that everyone has the opportunity to eat their food in kind of a circular manner. There's performance faults. So this is like the software not performing fast enough. This is a little less quantifiable, unless you need to say, oh, it goes exactly in this number of seconds or something. In general, this is how fast we need it it's more of a range. Recovery fault is a fault such that the program cannot get back into an operational state. There's software system faults, so this is your operating system crashes, maybe you access some inappropriate memory, or you do multi-threading incorrectly. For some reason, your operating system decides to shut you down. There's also standards fault. That's software that didn't follow the correct standards or requirements of whatever you might be working in. So that's all your different types of faults there. So moving on, we have kind of classifications for how you detect software faults. So this guy named Ram Chalargy, I'm not really sure how to pronounce that, to be honest. Anyways, he created this what's called an orthogonal defect classification when he was at IBM Research. And the idea is that it captures the semantics of software defects. So whenever a defect occurs, it automatically runs analysis on all this information to create kind of some statistics about that software defect, and this really gives you an edge whenever you do a root cause analysis to find out why a software defect occurred, because you already have all this information that allows you um, essentially saves you time, because you don't have to run analysis on this like raw data that has already happened for you. Really, really useful. So IBM, being a big research institution, during the research of this project, actually figured out that IBM Research is the largest non-governmental research body in the world. That is, there is nothing else in the world that has more employees, creates more patents, etc., than IBM Research. Anyways, they classify faults in a few different ways. This is not every single way they classify them, this is a lot of them. There's function faults, interface faults, checking, assignment, timing, building, and documentation faults. So we already covered a lot of these, but for instance, function faults are faults that affect capability, end-user interface, product interfaces, or global data structure. That's really your big one. If it affects the function of your program, that's a big issue. HP, another big software research giant, has their own kind of classification. Now, they start with the origin of where this fault occurred. I think that's a little naive. The reason being is that a lot of times the location of where software faults might present themselves is not necessarily where they started. So, for instance, like, just to make a parallel, if someone has a brain tumor or something, they might be feeling pain in their feet. Well, there's nothing wrong with their feet. It's all, it's in their brain. So similar idea here. Obviously, HP employs people much smarter than me, so I'll kind of defer to their wisdom on that one. So what's the kind of distribution of faults within, some given data? So I found another academic research paper called Common Trends in Software Fault and Failure Data. It was by researchers Hamill and Gazova out of the West Virginia University. So essentially what they did is they took these software change requests, that is the pull requests, on multiple large-scale NASA missions and their related software. So I'm assuming this is hundreds of millions of lines of code from all sorts of different NASA missions and their related softwares, like, rocket guidance software, landing software, launch sensors, UI systems for the astronauts to interact with, all sorts of different software. And what they found is that the vast majority of faults were requirements faults. They're a government agency. I'm sure they have a lot of strict guidelines they have to follow. And that accounted for almost a third. And then another third, practically, was coding faults. So I'm assuming that's everything from typos to algorithmic issues. And then they also have compiler faults and simulation problems, all sorts of kind of classifications, with the biggest three being requirements, coding, and then data problems, whether that be read, write, I/O issues, whatnot. And that was about almost 14% or so. So some testing issues. The way your test should be organized, the best practices really call for it to be organized by relevance. So for instance, all your test cases for your user input should be in one class. All your test cases for your algorithm robustness should be in another class. And the idea is that there's a certain attitude that when it comes to testing. In my first software engineering job, my manager kind of sat me down and actually talked to me about this. And she was essentially saying, like, well, a good developer should have this idea that I knew this would work. I created this algorithm and I studied it and I knew it would work. Whereas a good tester would have that attitude of, I knew this would break, and trying their hardest to make something break, essentially. Well, I found a really good blog, and it's in my reference materials, if you want to take a look at it. It's called Attitudes of a Great Software Tester. And the idea is that, these 6 attitudes should kind of encompass the mindset of a good tester. The most important being, I want to break this software at any cost. The idea is that your users are going to do everything they can in order to break your software, so you should try that too in order to find any bugs. You should have no compromise on your test quality, and you should really kind of acknowledge your position as a holistic part of like a software organization. So, in a testing team, there's a lot of different positions. A lot of times these names are a little ambiguous and kind of cross over, but in general, you have your managers. That can be like your test manager, your test lead. And then you also have your technical positions, your usability test engineer, your manual test engineer, your automated test engineer. And then you have a little bit more specialized roles like network test engineers, security test engineers. But in general, these are all names for people who will be writing tests on certain pieces of software. And then when it comes to most modern shops are object-oriented development, as I'm sure you all know. And so, in general, you're going to be testing that all your classes can be initiated, all your member functions work well. Pretty basic object-oriented lessons there. And in general, you're going to kind of follow this diagram of tests. You're going to write some code. You're going to run some tests on it. You might refactor those tests a little bit to figure out maybe you could write them a little better. Then you write new tests, and then you'll run those tests, and you'll see what went wrong, and you'll write your code to better it, and kind of so on and so forth. So what makes a good unit test? Well, a unit test should be able to verify a single unit of code. So these are small, independent modules, being able to call a single function, being able to create a single object, and making sure they all work well. And so the idea is that if you change a piece of software that's outside the scope of that test, it shouldn't affect that test at all. It should run quickly, it should be reusable. So how to write unit tests? Well, mostly it's done through frameworks. A lot of them are free or open source. Some more popular examples is Java has JUnit, PHP has PHPUnit. Google has their own C++ testing framework, and .NET has NUnit. So we're going to go through an example here of what writing a unit test looks like. We're going to be using Java and JUnit, and we're going to assume that there is a class called adder. There's a constructor called adder implementation, and adder just has a single function that takes two integers, sums them up, and then returns an integer. So here, with a few different things going on, just kind of from top to bottom here. You have your two packages that are just importing your JUnit framework. Being object-oriented, your tests are going to be in a class themselves. And then within a specific test, it needs to be named well. A test, that's really important part of writing unit tests is that you need to make sure that if someone comes after you in a new position, that they're able to distinctly see this test and understand what's going on. So essentially, you're just instantiating a new object of this class, and you're going to assert here. Now, assert will throw an exception if this line is false. So we're essentially saying, hey, we're going to add 1 and 1, and this needs to be equal to 2. If it's equal to 2, we can kind of assume your add function is working correctly for this input. And if that's not true, then assert, make an exception, say something went wrong. Now, an important part of the software is that you test a lot of different cases. So not just 1 and 1, but 1 and 2, and 2 and 2, and 0 and 0. But what happens when you add negative numbers, or positive and not negative, or big numbers? The idea is that you need to be able to test a lot of different cases. Good software tests all sorts of different random edge cases that you never think would actually happen, but you never know, your users might find a way. So fault recovery is the ability for a system to continue operating properly, not property, but properly in the event of a fault or a failure. So this is really important in real-time systems, systems that surgeons might use, or software that rockets might use, something that, lives could be at stake, and you need for it to be able to handle a fault gracefully. So a lot of times this is accomplished through redundant software, independent modules. There's a lot of other ways to ensure fault recovery. The idea is that you want to build in fault tolerance, which is the resistance of software to behave abnormally. You want that software to really, really try as hard as it can to act normally and predictably. This can be done through try and catch exceptions. Try and catch functionality as well as exceptions that kind of make your software a little stronger. So if you've taken Dr. Rigotti's programming languages classes, which is another class I really recommend, we learned a little bit about something called the Curry-Howard correspondence. And this is like an equivalence theorem that states that there's a direct relationship between computer programs and mathematical proofs. So you see right below this is the proof of commutativity of addition on natural numbers, written as I think this is SML, so functional programming language. But essentially, this is a proof, a mathematical proof, that is written as a programming language. The idea being is that if you can assert that some cases are this way before this algorithm was run, and assert that they should be this way after the algorithm was run, you have a pretty good basis to see how how this algorithm works and if it's upholding to what it should be doing. So how do you make a proof? Well, if you guys have taken discrete structures, you'll learn that inductive proofs are a pretty popular way. It's not really a proof itself, but more of a recipe for generating proofs. The idea being is that you try to prove some base case, like n equals 0 or n equals 1 or something. And then if n is true, then we can prove that n plus 1 is true. The idea being is that I might not be able to specifically prove that n equals 1,000 is true, but I can work my way up there from 0 and kind of prove in line. So the idea being is that once I have this framework in place, I can prove any n equals for, up to m using this deductive system. So what's the pros of doing it? Well, it significantly reduces bugs if you're able to correctly write a proof. Well, in order for that proof to be correct, there can't be any bugs in it. So that should eliminate the vast majority of them. Also, pretty easily give you some ways to improve the efficiency of your code. And of course, that proof itself is pretty good documentation. But there are some problems with trying to write programs as proofs. One of them is extreme overhead. It takes a lot of time and money and specifically trained people in order to write proofs. And on a complex system, it becomes pretty quickly unmanageable. So, for instance, like, I'm not quite sure how you would write a proof on, Facebook's communication systems. You might be able to do it on certain individual modules to work your way up, but once again, that's kind of a lot of overhead. And actually, there's another mathematical proof that says you cannot test any arbitrary input on any arbitrary program, for every input, that is. The reason being is that there's practically an infinite number of inputs for any non-trivial program, and it's just impossible to test every single input. Now, what that means in real software testing, that means is that you're never able to get 100% code coverage. So if your manager tries to tell you get 100% code coverage, show them the halting problem, and you'll be proven wrong pretty quickly. But that's not to say you can't strive to go as high as you want, or high as you can. So there's also this idea of component testing, and it says testing small individual components of a program with real data, opposed to just specifically calling methods and asserting. It's similar to unit testing, but it's a little bit more integrated, a little bit more holistic. It's making sure some components work together. So why would you want to prove something versus test it? Well, with proving is that you're proving the correctness of it. The whole idea is that you're trying to assert that it's correct and that there really shouldn't be any surprises, and you should be able to do that relatively efficiently, but as we said, that costs a lot of time, a lot of money, and you need experts to do it. Whereas with testing is that you're able to test for nearly all input types, at least. There might be some really extreme edge cases, but even then, like, you should be able to test for most use cases. And it saves your development time in the long run if you have some testing up front. And there's a lot of mature and popular frameworks. It's not like it takes a real advanced expert to write basic tests, and there's a lot of frameworks out there to help you do it. But just like any engineering, you're only going to be as strong and as good as the engineers themselves. If you have poor testers, you have poor testing. So probably the most important part of software testing is choosing the right test data. If you're feeding a system some amount of test data and you want to test that it works right, well, that data itself needs to be organized. It needs to be consistent. It needs to have both breadth and depth of possible scenarios. And more importantly, it needs to be based on edge cases and use cases. So we're not just testing random data. We're testing data that we assume our users will be able to create. If you have poor data, you're going to have poor testing and not going to have very good coverage. So a few different types of testing from a more high-level environment. So there's statement testing, which is literally testing the statement in each program. Let's say you have 100 statements in a program, and your test covers 70 of those statements. Well, you have 70% code coverage there. It's really good for checking code paths, but it gets pretty unruly pretty quickly. There's branch testing, which is a little similar to statement testing, but this focuses on your decision points. If you find yourself testing too many decision points, you're able to lower those. In general, you're going to simplify your code, make it a little bit more efficient, just better in general. There's path testing. So in path testing, your program is viewed as a CFG or control flow graph, and this uses cyclomatic complexity to determine the number of use cases, essentially. So with the known number of edges and nodes and connected components, you can use this formula to give you an idea of the number of paths or use cases that you have. There's all user testing, known as stress testing. So this involves having as many concurrent users access the system as possible. So whereas writing a proof on Facebook's communication systems might be pretty difficult, stress testing them is a much more appropriate way of testing, because you're able to see if that system can handle 50 million people accessing it and chatting all at once. So comparing the techniques, the main thing to take away here is that Statement and branch testing in particular are not able to scale very well. They try to test individual components, every individual component, such that any even moderately complex software is just going to have too many statements and too many branch decision points for that to really be tenable. User testing is really the only one that scales very well, which is, I think, why it's used in large, distributed systems. So there's integration testing. So integration testing is pretty much the opposite of unit testing. Whereas unit testing was all about testing individual components and making sure that they work independently, integration testing is all about making sure these components play nice together. So it's the building up of, at least bottom-up integration, it's the building up of testing from individual components and interconnected modules. So here we might test 4 by itself to make sure it works, and then test 5 by itself to make sure it works, and then works together with 2, and same thing with 6, 7, and 3, and making sure these all work together when running module 1. So that works well, but it doesn't work so well if you don't have all your components. And that's where top-down integration comes into play. This allows you to test your program as a whole, even if some of the components are missing. If you're pitching to investors, you might not be able to show them a fully 100% feature-filled final model, but if you do some integration top-down testing, you should be able to see kind of an idea of what the final product works like, which is great for, like, say, pitching to managers, investors, whatnot. Another type of integration testing is Big Bang. This is primarily what most of us students probably do, where we just write some code and run it and see, press play, see if it works. And then the most common way is sandbox testing, integration testing, where it's a little bit of everything, a little bit of bottom up, a little bit of top ground, a little bit of bang bang when you need it, or Big Bang when you need it. So sandwich testing is definitely the most common. Well, just like you don't just go ahead and start cowboy coding and running code without any sort of plan, same thing with testing. You need to have some sort of detailed document that outlines the strategies and methods that you're going to use to test the software. It acts as a basis for formally testing software. This would probably be more often seen in like a waterfall style engineering teams opposed to more agile teams that might have more loosely defined test environment. So an example is that you might have your introduction, talk about your test items, what features are you going to test, what features are you not going to test, the approach to test planning that you might do, suspension criteria, when you're going to stop planning, your test deliverables, your environment, and kind of your team or responsibilities, who's going to be doing what testing. So when do you stop testing? Well, one of the ways you can find out when you should stop testing is by doing what's called fault seeding. So the idea is here to intentionally plant bugs in your program to measure code coverage. So let's say you put a single bug in each 10% of your program and you found 8 of those bugs. Well, that's pretty good. That you can pretty confidently say that you had 80% code coverage. It's also good as an interview technique, so you can say, hey, find a bug in this software, bugs that you specifically planted in there. And it has a formula that you can kind of deduce your fault seeding and code coverage number, but I won't get too much into that. But the general idea that you want for fault estimating is that the number of defects you have is equal to the number of defects you had previously, just minus however many you fixed. Pretty simple estimation there. And then the number of unknown bugs in a software system is just an estimation based off how many the developers found, how many the testers found, and kind of the intersection of those two. So for instance, if your developers found 3 bugs, and your testers found 7 bugs, and 2 of those were already known, then you can estimate you had about 2.5, 3 bugs remaining. Obviously a very rough estimate. So your confidence in your software, well, this is kind of based off fault seeding, and this will kind of give you an idea of when you want to stop your testing. Your confidence level, once again, is kind of just based off how many errors you seeded, how many you found, and an estimation of how many might be remaining. And then a classification tree is this diagram that, based off your use cases, kind of helps you form how many tests you should make, what type of tests you should make, what you should be testing, your inputs, all that. And it's just based off your inputs. So if you have to put in size, color, and shape, you might have a certain number of inputs based off, how many different shapes or colors you accept and all that. So I think that's all. Yeah, this is my references section. So I hope you all learned a little bit about unit testing from my presentation. I certainly learned a lot. I knew a little bit about unit testing, but after this presentation, I can say I learned a lot more. So hope you enjoyed it. Thank you.